So, welcome now. Let us move to the next part, that is photoelectric effect. So, right now it is 3 a.m. here, and I hope you get the same energy from me. And now let us see that electromagnetic wave, when it strikes metals, electrons are ejected from metals. That is what we call photoelectric effect. But to happen so, there must be minimum energy in electromagnetic wave. Okay, we term that minimum energy as work function, and this work function is characteristic of each metal. Like sodium will have different work function, and other such metal will have different work function. So this is the basic schematic where the radiation is falling and electrons are ejected. Okay, and we have cathode electrode for the various experimental purposes, but the basic idea is that in photoelectric effect, whenever electromagnetic wave strikes metals, electrons are ejected. This effect was first discovered by Hertz in 1887, and the above setup yields the following result. Let us get very straightforward. We cannot waste time. So, if the incident electromagnetic wave have frequency less than some frequency, say V naught, then no photoelectron would be ejected. Suppose that if there is some frequency mu naught which is required and the frequency of the incident EM wave is even less than that, then photoelectric effect will not take place. Okay, and kinetic energy cannot go beyond a maximum value. That means kinetic energy has a maximum value, and kinetic energy do depend on frequency in linear fashion. Okay, and also let me tell you, the number of photoelectrons ejected per second is directly proportional to incident of the incident wave. Like whatever is the incident wave's intensity, okay, in the similar uh, proportion, you will get the number of the photoelectrons ejected per second. And photoelectric effect is instantaneous phenomena. Like as soon as you get the minimum amount of energy incident on the metal plate, then only exactly at that moment in the range of 10 to the power minus 9 second, okay, the electrons will be ejected. So these are our experimental observation. These are experimental observations. Now there is one very important question before us. Now question arises that key, we have four characteristic and we can ask key, is the classical physics which we used to know is explaining the effect? Okay, the answer is no. The classical physics, okay, cannot explain all four. Okay, if you want to be precise, only third point can be explained by classical physics. Okay, that is the number of photoelectrons ejected per second is directly proportional to incident wave. And let me tell you, apart from this lecture, if you want to put some of your own effort, then please look at Modern Physics by Arthur Beecher and Soviet Mahajan. Okay, but I think this note as of now is complete. So the question arises, okay, classical mechanics is not explaining three of the very important observations. So where did classical mechanics fail? So classically, there should have been no maximum of the kinetic energy, okay, because you know, kinetic energy directly depends on a kind of velocity, you may say, in the classical physics. Suppose that there is a mass of m, okay, and it is attaining velocity v, okay. So except the relativity, that is the maximum speed anything that can attain is the speed of light. There should have been no such limit, but there is a limit. Okay, so why there is a limit? Let us see. It should increase with intensity of incident electromagnetic wave, and kinetic energy should not depend on frequency. That's what should have been happened, because let me tell you, Force exerted by EM wave is proportional to electric field. Okay, and electric field increases with intensity and not frequency. If you understand the electromagnetic wave, okay, yeah, if you have read it well from Griffith book. In this book, it is very well explained. Okay, how does it depend on electric field? Okay, so that should have happened that E increases in the intensity, but practically opposite is happening. Okay, so that is why you know he that is why classically energy of ejected photoelectrons depends upon intensity, but in real it depends upon frequency. Okay, in real it depends upon frequency. Energy depends upon frequency. Also, let me tell you, classically, electromagnetic waves energy should be observed gradually, not instantly. Okay, but in real, it is happening very, very soon. Okay, experimental observation is in the range of 10 to the power minus 9 second. So this is happening almost instantly. Okay. Also, minimum energy must be there to eject photoelectrons, and that minimum energy must be greater than the work function. Look, at that time we introduced to some frequency mu naught. Okay, here this frequency. So what is this frequency actually? It is actually threshold frequency, or we have also corresponding value of threshold wavelength, and whatever is of this frequency, the same energy level is called work function. So work function is nothing but a kind of minimum energy required to energy minimum required to eject the photoelectron. So इतना एनर्जी होना ही चाहिए, then only photoelectric effect will take place. So now comes the great Einstein, and he tries to explain the photoelectric effect, and we all know why did he get his Nobel Prize. Okay, if you think that he get it for special relativity or photoelectric effect, then please confirm from Google. It is your task because they may ask us in interview. Okay, so he explained photoelectric effect based on Planck's quantum hypothesis. Recall that to explain blackbody radiation, Planck has proposed energy exchange in between radiation of frequency nu and walls of the cavity taking the quanta of h nu. Okay, Planck said that the energy exchange is happening, but it is happening with the quanta of h nu. For example, it will be exchanged in h nu for or 2 h nu or 3 h nu or in the same fashion integral multiple by h nu, but nothing in the fractional form. For example, it could not be 2 by 5 h nu. Okay, this exchange cannot take place. So this is what Einstein also used. Einstein also went further and explained the same idea in a different manner. He said that incident radiation itself is made of tiny bundles, and each bundles consist energy of h nu. Later, Mr. G. N. Lewis in 1926 called these photons. Okay, so photons was the term used by G. N. Lewis and not Einstein. Thus, as per Einstein theory, let me make it very clear again. Uh, Photons are bundles of energy of h nu, and when it collides with electron in the metal, the energy is absorbed by the electrons and electrons are ejected. So energy exchange is taking place basically in the photoelectric effect. So if I call you that what is photoelectric effect? So it is the phenomena where the energy exchange is taking place. Energy exchange is taking place. So you must remember that. Also, but the minimum energy of photon must be greater than work function. Then only photons will be ejected. So minimum energy must be the work function of the metal. And different metal will have different work function. Let me write it. Different metal have different work function W naught. So what is the application of photoelectric effect? So let me tell you, photo cell, photo multiplier tube, solar cells is a very prominent thing. Okay, we often come to study in current affairs about International Solar Alliance. Okay, so that is a very prominent example. Then we have light dependent resistor. Okay, and also we have in scintillation counter. So these things are application of photoelectric effect. If you add such an application to your answers in mains examination, you will probably get half or 1 marks more than your competitors. Now we have some solved examples of photoelectric effect. So let us see them quickly. Find the number of photons emitted per second by a 40-watt source of monochromatic light of wavelength 6000 ampere. So look, 40 watt, what is nothing but power, and power is nothing but energy per unit time. That means in a single second, in 1 second, 40 joules of energy are being liberated somehow. So it is not the energy of one single electron or one single photon. So there must be n number of photons, and n is multiplied with the energy of one photon. Number of photons, and hν is what? Energy of one photon. And this is what? Energy per second, which we calculated just 40 joule per second. So n is actually E upon hν, and value of E is 40 joule, and hν is hc upon lambda. And when you put all the value and do all the calculation, you will get n to be 12.06 multiplied by 10 to the power minus plus 19. Now there is another question. The work function of photosensitive surface is 3.2 electron volt. Look, electron volt is actually the unit of energy. Okay, so it is work function. Now let us see. That question is, will photo emission occur if the photon energy of 3.8 electron volt is incident on the surface? If yes, find in joules the maximum kinetic energy of the photoelectric effect. So let me tell you what will happen. We will check if our energy of the incident energy, photon energy, is more than that or not. More than that means more than work function or not. So 3.2 is less than photon energy. So that means the energy of photon is more than the work function, which means the photoelectric effect will happen. So it will happen. So since energy of photon is 3.8 electron volt, which is more than the work function, okay, so photoelectric emission will happen. Now for kinetic energy, what you need to do? You need to do what is your usable amount of energy. So usable amount of energy is this much subtracted. You must take out the work function, the minimum requirement out first, and then you are getting 0.6 electron volt. That is what is kinetic energy. This much energy will be only gained by electron. Okay, so done and dusted. Now let us move to the third question, that is work function of a metal is 3.45 electron volt. So what is the maximum wavelength of a photon that can eject an electron, okay, from the metal? So we have work function. So we put work function. So maximum frequency you got this, okay, and sorry, it is written here minimum frequency. It could not be minimum. There is typo. I mean writing error. It could be maximum. Because work function is directly proportional to h nu na frequency. Work function is directly proportional to frequency. So frequency is going to be maximum for the work function to become more, but wavelength could be minimum because that is inverse relation. So corresponding let me rephrase the question once again. Maximum wavelength of a photon that can eject an electron of a metal. Okay, they are asking maximum wavelength. Okay, so let me think, then I will make it clear. Work function of a metal is 3.45 electron volt. That is very, very fine. We get frequency from here. Okay, and what is the maximum wavelength of a photon that can eject? Okay, so they are asking, so what will happen? We will have, we will need this much minimum amount of frequency for the photon to eject electron. That means this is actually the maximum frequency, but this maximum frequency must be the minimum uh, frequency requirement for incoming photon, condition for incoming photon. कि भाई फोटोन जो आ रहा है उसके पास कम से कम जो है ये जो वैल्यू जो आ रही है हमारी, है ना, इतनी फ्रीक्वेंसी होनी चाहिए। दैट मीन्स उसकी इतनी एनर्जी तो होनी ही चाहिए, और उसका जो कॉरेस्पॉन्डिंग वेवलेंथ होगा फिर वो मैक्सिमम हो जाएगा, क्योंकि वो इन्वर्स जाता है। अगर फ्रीक्वेंसी मिनिमम हो रहा है तो वेवलेंथ को तो मैक्सिमम होना पड़ेगा, यानी वेवलेंथ इससे ज़्यादा नहीं हो सकता। तो मैक्सिमम वेवलेंथ जो इस हिसाब से आएगा, when you will calculate it, you will get 359.42 nm means nanometer. Now let us move to the next question. A metal of work function 3.0 electron volt is illuminated by a light of wavelength 3000 angstrom. So threshold frequency you need to calculate. Okay, the maximum energy of photoelectron and stopping potential. So this is the new question here, stopping potential, and I did tell you that we will learn by doing also. So let us do this question. So threshold frequency will come from work function formula. Work function is actually h nu, and this is threshold frequency, TF, threshold frequency. So nu is simply work function divided by h. We did it, and we got threshold frequency to be 7.2 multiplied by 10 to the power 14 hertz. Now frequency of the incident radiation would be simply C upon lambda, and we have wavelength of incident radiation already, which is 3000 angstrom. Okay, so we followed simply the formula, and we got frequency to be 10 to the power minus 15 per second or hertz. Okay, and a maximum kinetic energy. So maximum kinetic energy of the photoelectron is simply energy of the photon minus work function. Okay, we get this energy of photon, and this is work function. Anyways, calculated, we got the maximum is this much. Okay, so now we are required to calculate the stopping potential. A stopping potential is the potential which we must apply so that the electron is repelled. Okay, in this setup. Look. Okay, here we must apply such a potential that this electron is actually repelled and it does not move, it stops. So hence it is named stopping potential. Okay, so we are required to find that also. So in that way, and it is countering, it is stopping potential is actually countering the kinetic energy. Okay, so in this way you will solve it and you will get it to be 1.14 volt. So if you apply 1.14 volt across it in a obviously electromagnetically satisfying condition, okay, that means the direction of the potential so should be such that uh, it does not accelerate the electron, but it actually stops. Okay, so we'll have to take care of cathode electrode, but that is the case of the experiments as well. Right now here we are concerned with just theory. So now we have next question. A ray of UV light of wavelength lambda, which is equal to 3000 angstrom, falls on metal work function 2.28 electron volt, and it is ejecting an electron. So what is the velocity of the emitted photoelectron? So for velocity, you know, in such condition you may find the kinetic energy. Okay, and kinetic energy could be used to find the velocity. Okay, so use this and do it at your own. We have next question, which is of similar nature, which is not very much tough, so you will do it yourself. This question is important. Okay, and I will explain it later on. Right now we need to move forward, and let us see that is there any similar question on that or not. Okay, now we are done with the photoelectric effect. So now what we are required to study? We are required to study Compton effect. So let us meet in the next part of this lecture.